This is section 3.3 on formula weights, and I think for the most part, everyone's going to remember this one from high school because that is generally covered in high school. It tells you about the periodic table. And when we have the periodic table, it is a weighted average. Back in chapters 1 and 2, we talked about isotopes, we talked about mass spectrophotometry. So again, this will be something that you may already be familiar with. If I look at a periodic table, the element carbon has the atomic mass of 12.01, and it's atomic mass units, but you may hear me refer to it as grams per mole. It's just something I do automatically. If someone were to give you a percentage for each of these isotopes, how would you go about finding that atomic mass? Well, you'd convert the percentage to a decimal, and you would just take that peak, the peak at 12. You would convert 1.07 to the decimal, and you would multiply it by 13. Now, I really don't know where that other number came from, but we're not going to worry about it here. And when you would do the math, that's where you would come up with the atomic mass, the weighted average on the periodic table. So we covered that back in chapter 2. Now here in chapter 3, we're going to need to do stoichiometry. So we're going to talk about a formula weight, and a formula weight tends to refer to an ionic material, something like sodium chloride. If we talk about a molecular weight, we're going to be talking about a molecule, and I picked something sweet. I picked sugar. I know this may be a review, but again, let's make it a review where everybody is on the same playing field. If I look at sodium chloride, I will look at my periodic table. And from it, I will extract that sodium has an atomic mass of 22.99, and chlorine has an atomic mass of 35.45. There's only one of each element, so it'll be 22.99 plus 35.45, and that's going to give me a value of 58.44 atomic mass units. And again, I will probably just call it grams per mole. That's just the way my brain works, and that's how your brain will work as time goes on. If I look at my molecule, what's different? Well, the sweet sugar molecule has subscripts. Carbon on the periodic table has a mass of 12.01. Hydrogen has a mass of 1.008. And the element oxygen has a mass of 16.00. All I'm going to have to do here is take into account the number of atoms. 6 times 12.01 for carbon, 12 times 1.008 for hydrogen, and 6 times 16.00 for oxygen. I've encouraged you to keep a notebook, and it really is important. Put down your intermediate answers. It makes it much easier to go back and see where you might have erred. And I come from industry. And in industry, we can't have concepts. You do have to have the data, okay? And I'm sure many of you, that's where you're headed, to some sort of job in business. Here we have 180.6 atomic mass units. That is the molecular weight of sugar. C6H12O6, I should say one of the forms of sugar. So this will not be a question on your exam. What wave our hands and talk will be a question on your exam is giving a percent composition. So that is for any element that's in the formula. You take the number of atoms, you multiply it by the elemental weight, and you divide it by the formula weight and multiply by 100%. So how does that come about? Well, let's work the problem together, okay? So for this problem, I would start by saying, let's start with copper. I have one copper atom, and it weighs 63.55 atomic mass units. I'll get the number 63.55 grams. For my nitrogen, oh, I guess I forgot to say, I just moved on and on. What is the formula of copper nitrate? What if they give it to you that way? You have to say copper nitrate is CuNO3 2. Copper 2 plus 2 charge, nitrate minus 1 charge. You need to be able to write the ionic formula. Oh, skip that. Nitrogen, 2 times 14.01. I come up with a total of 28.02. And for my oxygen, it is going to be 2 times 3, 6 times 16.00, which is going to give me the number 96.00. When I add them together, 187.57. I would encourage you to do it this way, because now when we need to find our different percentages, for my percent copper, it's easy. Only 63.55 grams over 187.57 grams, multiply by 100, and we come up with 33.88% copper. Now, the problem asked for 3 significant figures. So again, what you learn in Chapter 1 and Chapter 2 carries on over here. Percent nitrogen. I'm not going to do 2 times 14. I'm just going to pull my number 28.02 grams, and I'm going to divide that by 187.57 grams, and I'm going to multiply it by 100. And I'll come up with the value 14.93% for my nitrogen. And my last is my percent oxygen. I will go 96 grams divided by 187.57 grams, multiply by 100, and come up with 51.18%. Now, my gut feel is they're not going to ask you for all 3, but I do them here because I want you to see that they have to add up to 100%. So keep that in mind when you're working a percent composition problem. So again, facts are used here, a method is used here, we're solving a problem. My goal is not just to solve problems with you, but to give you some insight. So we just did copper nitrate, and copper nitrate in the presence of air, it picks up 3 molecules of water to make a brand new crystal structure. It will have a new, I'm going to call it molecular weight because that's how my brain works. And when I calculated it out, it was 241.60 grams. So how does my percent copper change for the hydrate? Well, let's kind of make a little chart here. If I have my percent copper, it used to be 33.9%. For this new material, 26.3%. If I look at my percent nitrogen, it used to be 14.9%. Now it has dropped to 11.6%. If I look at my percent oxygen, it was 51.2%. And in this new material, it is now 59.6%. Percent hydrogen, okay, there was none at all in copper nitrate, but when it picks up those waters, 2.5% hydrogen. So how does the mass percent copper change? Like, these are things to pick up as you go through these science courses. Notice both the percent copper and the percent nitrogen, they are going to decrease. And you can kind of see why. We have added more O, and we have put in new hydrogen. So again, insight, thinking about, oh, these calculations have to be done, but what happens when something changes? The other thing I have here, this is an old midterm question. It will be worked during the Zoom lecture and then posted. It says, calculate the atomic mass given the isotopic abundance data. So if you've done some problems, think back to Chapter 2, think of the beginning of this section. That percent abundance needs to be multiplied by an atomic mass, and that will give you the atomic mass.